Welcome everybody to another episode of Functional Programming 101. And today we're going to talk about declaring types and classes ourselves. Up to now, we have only in the lecture on parsers, we have defined types ourselves. But for the rest, we kind of have assumed that the types are there. For example, we have assumed that the type list exists, and we have assumed that tuples exist. But of course, just like we can define new functions in Haskell, we also want to define new types. And what we're going to do in this lecture is we're going to show how to declare new types and how to declare new type classes. But also, I'm going to compare and contrast this with typical object-oriented programming, how these things work there. And what you will see is that although the syntax is a little bit different, a lot of the ideas are very common. And this is a general thing that I like to do. Instead of emphasizing the differences, I think it's often much more productive to emphasize commonalities, okay? And maybe, you should try this too. As programmers, we often kind of go, well, but, no. It's much more productive to say yes and to emphasize, what is common. And so I'm going to try to do that here. And please take that as a meta lesson for this lecture. All right. In Haskell, we can define an alias for an existing type by saying type string equals another type, or type, new name equals another type. And in this case, we are defining string as an alias for a list of characters. And this is an idea that we have used throughout all the lectures, right? Every time we saw a string, we treated it as a list of characters. But in types, we often wrote string, because that's what we wanted to convey. But when we were coding against strings, we want to see them as a list of characters. And here, this type declaration achieves that. This is just another name for this type. Good. And what we often do is we use this, just like with string, we use type aliases to convey the meaning or our intent of what we want to do. For example, instead of having a pair of integers, we can say, well, we declare this as type position. And then instead of, writing int, int everywhere, we can write position. So the origin, that's at coordinate 0, 0. And then we want to kind of, move a position to the left. So this is a function that takes a position and returns a new position. And it takes a pair x, y, and it subtracts 1 from x. All right? And now, by looking at this type, you get a better idea of what it's doing. And the fact that we're using pairs to represent positions is really just an implementation detail. Another example here is a parameterized type alias. So here we define the type of pairs of type A as pairs of type A. See? So the type of pairs of values of type A are pairs of values of type A. And now we can define functions over that type. For example, we can take a pair of integers and return an integer by multiplying the two. Or we can take a single value and copy that into a pair. And there's the function copy, which takes an x and returns a tuple that contains another copy of x. Type declarations, of course, can be nested. So if we define position as a pair of integers, then we can define another type synonym to mean position to position. So a transformation of a position is a function that takes one position and returns another position. So in this case here, we could have defined this function here to have type trans. Now there's one important thing here, is that these type synonyms are really just synonyms. They're just abbreviations, and which means that they cannot be recursive. So in this case, when you define type tree to be a pair of an int and a list of trees, this is not allowed. And when you can define, and we will see that later, it's no problem to define recursive types in Haskell, but they always have to go via a nominal type. And this is a restriction that many languages have. If you have an object-oriented language, typically it has a nominal type system, and that makes it easier to check whether two types are equal or one type is a subtype of another. And if you have purely structural types, that becomes a little bit more difficult. So it's, that is typically the reason for that. But if you're interested in programming language and type systems, the field of structural versus nominal types is a very interesting field, and you can spend years researching that and reading papers on it, and get a PhD in that area. What I said is, when we want to make a recursive type, we have to go through a nominal type. And the way we define nominal types in Haskell is via data declarations. So here we're defining a new type named bool, and it has two constructors, true and false. Okay? And these constructors are, since they don't take arguments, they are at the same time values. If you know Scala, you will see that Scala case classes are very similar to algebraic data types. But if even if you don't know Scala, but say you know Java or C#, one way to look at these data declarations is as follows. This is an abstract base class, bool, and then the types here on the right-hand side are the subtypes. So false extends bool, and true extends bool. And since bool itself is abstract, you cannot create an instance of bool. You can only create instances of false and true, but both have type bool. And in Haskell, true and false don't have their own types. They always have type bool. So that's even simpler than having an abstract base class and two derived types. As I mentioned, the values on the right-hand side there, true and false, are typically called constructors. And with the explanation I gave with the abstract type and the subtypes, that makes sense. They correspond to constructors in an object-oriented language. In Haskell, type and constructor names must begin with an uppercase letter. So functions and type variables begin with a lowercase letter, and types and constructor names must begin with an uppercase letter. And these algebraic data types, another way to look at them are as context-free grammars, where the thing on the left-hand side is a non-terminal, and then the right-hand side can contain terminals, which are the constructors that themselves can recursively contain other types, like a grammar contain recursively on the right-hand side non-terminals as well. Here's an example of a slightly more interesting algebraic data type. It's like a Boolean thing with three value Boolean. So we have yes, no, and don't know. So this is maybe like SQL, where this is like, null. So this is a three-valued logic. And now we can use this thing to say, I want to have a list of answers, yes, no, unknown. And now I'm going to define another function that flips the answer. So this is like the generalization of negation. If I have yes, and I flip it, becomes no. If I have no and I flip it, it becomes yes. And if I don't know and I flip it, I still don't know. All right, so if you're familiar with SQL, this will be very similar, where unknown plays the role of null. Here's the standard OO example of circles and rectangles and shapes. In Haskell, it looks as follows. We have an abstract base class shape and two subtypes, circle and rectangle. Both of them are shapes. And in Haskell, circle and rectangle don't have their own types. So when you create a circle using the circle constructor, you get a shape. And if you create a rectangle using the rectangle constructor, you also get a shape. All right? So that's the main difference between algebraic data types in Haskell and the way you typically write inheritance hierarchies in an OO language. Now we can use this constructor to create a particular shape, a square. So we take a value for the first coordinate there, and we create a shape by just duplicating that value here. And we can compute the area of a shape, and that will return a float. And so here you see that area is defined on shape. Okay, and then we do a pattern match here, which is very much like doing a dynamic dispatch. So if the shape happens to be a circle, then I take pi times r squared. If the shape is a rectangle, I just multiply the sides. Okay, but so pattern matching kind of corresponds to virtual dispatch when you think of algebraic data types as object hierarchies. Now, when we look at these constructors that we define in here, they implicitly define constructors, functions that take a float and return a shape, and a second function that takes two floats and returns a shape. And these functions are called circle and rectangle. So if you look at the type, if you ask :t of circle, Haskell will tell you float arrow shape. And if you ask what is the type of rectangle, it will tell you it's a function that takes two floats and returns a shape. Okay? So again, the analogy with objects is still intact. You define your subtypes, and really what you get for free is a constructor to construct these types. We mentioned the maybe type a couple of times. Maybe type is like a list that's either empty or has a single value. Usually convenient to just use list, but if you really want to use the maybe type, maybe you're an F# person or an ML person where maybe is used a lot, well, you just define a new algebraic data type. Maybe of A is either nothing or just an A. And now we can define a lot of functions that people are kind of proud of, because we can take a list and we can take the head, but if the list is empty, we return nothing. And if the list is not empty, we take the head and we return just. Now, I'm not a big fan of this kind of definition of head, because we're now still stuck with this maybe. So you really have now reduced a list to a singleton list, but you have not really gotten the head out. And in order to kind of go from a maybe of A to A, you will still run in the same difficulties as you had when you went from a list, from an empty list to A with proper head. Okay, so that's why I typically don't care about this maybe type. It stands in the way. It doesn't help you, because at some point you have to get rid of it anyway. All right, that was the end of part 1. Let's take a short break, and I'll see you soon for part 2.